I'm Fred.
I'm Mark.
I'm Phil.
We're going to take you through an installation of a TA-025 Bosch geothermal unit.
So here we have received a Bosch TA-025 geothermal heat pump at the site. Our first step is to check the machine as it was shipped on the pallet to make sure that we have no visible damage. Our next step will be to remove all of the shipping materials, the packaging and the wrap, and remove the machine from the pallet. Then we will go through the installation process.
This particular installation is in a very large mechanical room. So we've got a lot of room to work with. You notice that the unit is already on the isolation pad. We've taken it off the pallet and we're ready to now get inside the unit, open up the panels, take out the foam shipping block that is underneath the blower wheel, and get ready for the installation process. Bosch vertical units are developed and manufactured from 2-ton to 6-ton, left or right hand return. This particular system is a right hand upflow unit. Now I'm going to take off the top panel, the blower section first. This panel is removed first, and then I'm going to go into the electrical section. Inside the blower compartment is the ECM drive blower motor. It is protected in shipping by the styrofoam shipping block. It must be removed upon installation. I removed the Molex plugs from the ECM drive blower motor to make the styrofoam block removal easier. Now I'm going to reply these back into the ECM motor.
Once the shipping block has been removed from the blower assembly, you can now take the lower access panel off of the equipment to give you access to the electrical and mechanical part of the equipment, so that we can now loosen the compressor mounting bolts that have been tightened down prior to shipping. Next thing we're going to do is remove the installation instructions from the electrical box. Every step of the installation instructions should be followed throughout the installation process.
Always locate the unit in an indoor area that allows easy removal of the filter and access panels and provides enough room for service personnel to perform maintenance or repair. On horizontal units, allow adequate room below the unit for a condensate drain trap and do not locate the unit above supply piping. Remember, these units are not approved for outdoor installation. Therefore, they must be installed inside the structure being conditioned. Never locate these units in areas that are subject to freezing.
All equipment equipped with factory installed electric heaters requires 2 power sources. You'll notice that we have 2 disconnects on the wall. One of the disconnects takes care of power for your heat strips, for your blower operation, and also for all of your low voltage circuits. The other disconnect supplies power to your compressor contactor. At this point, we're going to show you where those connections are made on the equipment. There are several electrical openings on the right side of the cabinet. There are concentric openings so that you can make your high and low voltage connections to the equipment. For your heater connections, there is a knockout located on the top of the cabinet. Will give you access to run your wire into the electrical box for the electric heaters. There's a terminal block located in that box for you to make those connections. And connections for your compressor contactor are located down in the electrical compartment in the lower access panel. You'll make those connections to the compressor contactor at terminals L1 and L2. We'll also at this time run our power supply for our circulating pumps, and we will wire those connections up to T1 and T2 of the contactor. This will allow the circulating pumps to operate anytime that the equipment is operating. Once we get those connections made, we will make our low voltage connections. There's also a concentric adapter in the front with the grommet already installed. We'll make those low voltage connections at a terminal board that is located on the ECM motor control board. You can see at this point that we've made our high voltage connections at L1 and L2 from our power supply. We've also made our circulating pump connections at T1 and T2. Up here on our ECM motor control board, our low voltage connections are completed. At this point is a good time to go ahead and set up the dip switches and the jumpers on our control boards. On the ECM motor control board, you have 4 sets of jumpers. You have an adjust jumper, you have a delayed jumper, you have a heating jumper, and a cooling jumper. The heating, the cooling, and delay jumpers should be placed in the proper position for that particular unit. In the installation manual is a chart that shows you which position all 3 of those jumpers should be in for that particular model. If they are not in that position, when you operate the unit, the ECM motor will not operate correctly and the LEDs will flash erratically. So please consult the installation manual and make sure they are in the proper position. The adjustment jumper is going to come from the factory in the normal position. This will give you your normal selected nominal CFM. There is also a plus and a minus position. The plus position allows you to increase CFM by 15%, and the minus position allows you to decrease CFM by 15%, depending on where the heating, cooling, and delay jumpers are located. The test position allows a service technician to place the jumper in this position, and on a G call or fan only call from the thermostat, operate the ECM motor at 100% to make sure that it is functioning properly. On the UPM control board, there are 6 dip switches. You should consult the installation manual to determine the proper position for each of these switches so that all of the safeties will function properly. The first switch at the top of the board is the freeze protection switch. It is going to come in the no position, which means there is not a factory installed option of freeze protection. If you have the factory installed option of freeze protection, you need to put this switch in the yes position so it will be functional. The next switch has to do with the temperature cutout of that freeze protection. There are 2 settings, one at 35 degrees and one at 15 degrees. 35 degrees should be selected for systems with water in the loop. 15 degrees should be selected for closed loops with antifreeze in them. Switch number 3 has to do with your lockouts. There is an option of 4 soft lockouts and an option of 2 soft lockouts before the system goes into a hard lockout. Switch number 4 is a reset option. In the factory position or Y position, you will be able to reset the hard lockouts from the thermostat. In the R position, the power must be reset in order to bring the system out of a hard lockout. Switch number 5 has to do with alarm outputs from the board to an LED or a service indicator light on a thermostat. You can select either a continuous 24 volt output to that terminal or a pulsing output in 24 volts AC to that LED. The last switch is a test switch. This allows a service technician to place it in the yes position and override the time delays while he is diagnosing problems in the system. You always want to remember, once you finish servicing the unit, to put that switch back in the no position so that all the time delays will be active and the system will be protected from short cycling.
What we're showing here is the pipe penetration coming through the brick wall. Notice that we have the white pipe, that is a sleeve pipe. These 2 pipes are connected to our header pit that is outside in the backyard. This is a parallel reverse 3-ton header pit. So what you're seeing here is that water goes in, water goes out, water travels down each one of these circuits at the same flow. Now that our loops have been pressurized and tested for leaks, we are now ready to finish the process of the polyethylene pipe fusion. We're going to set in this particular system a prime tank and also a OEM 1-pump flow center.
We have now mounted the new Bosch GeoPrime 2.5 gallon accessory that we can use in conjunction with our flow center. Our flow center will mount just below our GeoPrime tank. This allows us to operate the system as a non-pressurized system. It has a small reservoir on it, and you can see the sight glass here and a cap on top where you can add fluid to the system, as your pipe expands and contracts or as you require more fluid. Also has a set of isolation valves located on it so you can isolate it from the system while you are doing your flushing and purging processes. Right below this, when we mount the flow center to the GeoPrime tank will come with a set of adapters. They are double O-ring adapters, and you have to lubricate those with the lubricant that comes in the kit. You just simply apply the lubricant to the O-ring seals and then apply the fitting to the opening on the bottom of the GeoPrime tank. There's a threaded fitting that attaches it to the prime tank and another fitting on the bottom that attaches it to our flow center. And you only want to hand tighten these fittings. You don't want to use any kind of wrench on there, and make sure that you get a good snug fit, but just hand tight only.
Mark, we need to do some 1.25" fusion. So what I'm going to do is I've got some pipe cut here. I'm going to go ahead and do some chamfering of the end. Thanks for handing me that code ring. And the iron is what temperature?
We are right at 500 degrees.
500 degrees. Let's go ahead and check that. I'm not going to check it on the face, and I'm not going to check it on the tool itself, but I'm going to check it on the outside part of this. And we are looking like we're really good, 500 degrees. We're going to hold this 1.25 inches on the tool for about 17 seconds. This is our timer. I've got 3 seconds to put it on, and then I'm going to hold it for about 60 seconds to make sure that it sets up, and we're not going to play with it or anything like that for about 10 minutes. But that is an 1.25 inch HDPE pipe fusion. Will not leak. And that's the first one of many on this geothermal job. We've got the one pump flow center mounted on the wall. And now we're going to take our flow link connection kit and we're going to open it up. This particular kit is a 3/4 inch. The items in the kit is a 10-foot section of 1-inch rubber hose, stainless steel hose clamps, 2 Pete's ports devices, 2 brass 1-inch to barb and 3/4 inch MPT connection elbows. The flow center will normally be set within 5 feet of the equipment. Thus, this 10-foot rubber hose inside the box will be cut in half. Inside the box are double O-ring fittings to barb. The barb fitting is going to go on the hose. The double O-ring fitting is going to go inside the flow center. Also inside the box are the elbows. Barb fitting goes onto the hose. This fitting is going to get Teflon taped and go into the geo unit. Never use adjustable style grip tools. Always use the proper tool on the brass fittings. It's important to make the right water connections. Always verify the water flow on the flow center and the water flow on the unit is correct. The hose may need to be insulated to eliminate condensation issues.
Next, we're going to make our electrical connection to our circulating pump. This is our wire coming from our unit that is wired into the compressor contactor to terminals T1 and T2. This is the electrical box on top of the pump. You simply remove the screw on the electrical box and remove the cover. There are 2 wires to make your connection to. There's also a grounding screw back behind the capacitor. Now you just insert your wire through the electrical knockout on either side of the pump housing. There's an additional knockout on the other side. Connect your electrical fitting to the electrical box, and then using some field supplied connectors make your connections to the 2 wires on the circulating pump, as well as making sure that you attach the ground to the grounding screw in the electrical box. At this point, we're going to install our thermostat. We have already made our thermostat connections at the equipment on the low voltage terminal block located on the ECM motor control. We have several thermostats available from Bosch, anywhere from a simple digital control to the programmable thermostats that are actually touchscreen. And any control that you use, you want to make sure you select the control that matches the number of stages that you have to operate with your equipment. In the case of the TA25, which we're installing today, it is a 2-stage heat and 2-stage cool unit. It also has an additional 3rd stage of heat that is factory installed, that is the heat strips. So we will actually have to have a thermostat that is capable of 3 stages of heat and 2 stages of cool. Now, if you're in an existing home and just replacing a system, the thermostat will already be located in the home somewhere near the return air, and you'll just simply have to replace that control. If you're on a new installing a system in a house that does not have an existing system, then you'll have to route your thermostat control wire to the location where you want to mount that thermostat. We have already routed our thermostat wires to where we want to mount our thermostat near our return air location. And we've routed our thermostat wires through the hole in the back of our thermostat subbase. And we've made our connections to the thermostat subbase electrical connections. You want to make sure that the wires that are connected here match up with the same terminals on the TA025 unit so that we get proper operation from the thermostat. And once you've made your electrical connections, you can simply just put the thermostat or attach the thermostat to the subbase. And then once power is applied to the unit, the thermostat must be configured for the number of stages that you need for the TAO25. So always consult the installation instructions that come with the control to program the stat, and consult the installation instructions that come with the unit to make sure you wire it correctly. Next thing I'm going to do is pipe up the condensate drain. All of the units that we produce are going to require a trap and the drain outlet, so make sure you select a trap that is deep enough to overcome any static pressure that could be caused by the blower. Typically on variable speed models, you want something that is at least 2 inches in depth from your outlet to the outlet of your trap, and then another additional 2 inches from the outlet of your trap to the bottom of the trap. So make sure you select the proper trap for the application, and also make sure you follow your local codes and how you pipe these up. There may be some additional requirements for condensate trapping in your area, such as clean out tees and vents and those types of things. It's always a good idea to dry fit everything before you glue it together. So the first thing we'll do is we'll go ahead and apply some Teflon tape to our male adapter. We'll take the male adapter and thread it into our female fitting that is attached to the front of the unit right between your two water loop connections. Once we have that tightened down, we will cut a couple short pieces of PVC, attach our trap to the fitting to the male adapter on the front of the unit, and then we'll take a 90 out behind the unit to connect to our existing drain line. You'll always want to make sure that you have sufficient slope. Usually want to follow code, but 1/4 inch per foot is a good rule of thumb to make sure you get good drain from your condensate.
What we've done is we've installed this supply plenum on top of this unit. The dimensions for this supply plenum is in the spec manual. We put some foam insulation in between the plenum and the top plate so we don't have any air leakage. You notice that we have some screws located in the top plate going around the front side and also the left side of this. Notice the different locations of these screws. This is through the top plate of the unit. This is through the duct flange. Right underneath this top plate is the evaporator coil. Never want to screw down this way. Always screw horizontally going toward the duct flange. A supply flexible connector is recommended on all metal ductwork systems.
Notice now that we have installed the return air plenum. We also have installed a flexible connector, assuming we're connected to metal ductwork also. When sizing either the supply or return ductwork, current ASHRAE standards and criteria must be followed. It is always recommended with metal ductwork that we insulate with at least 1 inch insulation, either internally or externally, to prohibit any type of condensation, especially during the cooling cycle.
The HRP heat recovery package at Bosch, it is a factory installed option on the Bosch TA product. Its design is to take the excess heat generated from the compressor, and through the water to refrigerant coax, the heat will be transferred to the potable water storage tank for use. The internal electrical schematic will show a 240 volt circulator, a 140 degree hot water limit, and a combination on-off 1 amp circuit breaker switch. The use of the HRP in the summertime will increase the efficiency of the equipment. The installation of the piping of the HRP from the unit to the storage tank is recommended to be total copper tubing. The industry will want to run flexible PEX style line. In this case, Bosch recommends that the first 14 inches of the water out of the unit to be copper tubing. All tubing will never need to be smaller than the diameter of the water connections on the equipment. Please insulate the piping as needed. The installation manual of the HRP will show upon commissioning the water circuit must be void of air. You can do this by the air release valve inside the unit.
The next part of our installation process is the flushing and purging of our heat exchanger and also the system side of our water piping. This is the new GeoFlow flush cart. It is available now through the Bosch accessory catalog. It incorporates a 1.5 horsepower pump, a built-in on-off switch with a ground fault interrupter on it, a 20-foot cord. It is 120 volt. It also has a reservoir tank on it and a series of valves that allows us to fill this reservoir, pump water through our loop system, and flush and purge flush all the debris out and purge all the air out of the system.
For this system, we'll be using a water-only solution because this installation is in a southern climate and the minimum entering loop temperatures never drop below 42 degrees Fahrenheit. In areas where the minimum loop temperatures drop below 42 degrees Fahrenheit, or when the piping will be routed through areas subject to freezing, an antifreeze solution is required. When using an antifreeze solution, we'd have to calculate the freeze protection percentage based on the total volume of fluid. For more details on this process, please reference the installation manual. The first step is to remove the flow center flush port caps and then remove the double O-ring flush port plugs. Next, install the 1.5-inch double O-ring flush cart connectors. Be sure to lubricate O-rings prior to install. Next, attach the return hose connection of the flush cart to the water inside of the flow center, and then make your discharge hose connection to the water outside of the flow center. In order to properly purge the ground loop, we now have to adjust the position of the factory set 3-way valves on both the Geoprime tank and the flow link pump center. Starting with the Geoprime tank and using a 3/8 inch drive, isolate the prime tank by rotating the 3-way valves from the operation position to the bypass position. Adding any sort of water pressure to the Geoprime tank during commissioning process will void the Geoprime warranty. Next, rotate the flow center 3-way valves so that the off marking is set to the 6 o'clock position, thereby isolating the flow center and the heat pump from the ground loop. Now we need to verify our flush cart is set up properly. Verify the screen filter inside the reservoir is strapped to the PVC return pipe. At this time, all ball valves on the flush cart should be set in the off position. Connect the 20-foot flush cart power cord to a grounded 120 volt 15 amp circuit. Attach garden hose to the GHT swivel adapter on the flush cart. Open up the garden hose ball valve in order to add fluid to the flush cart reservoir. Open up the 1/4-inch pump case drain port valves in order to bleed the air and prime the pump. Flip on the GFI power switch. As the water drops, add more by opening the 1/2-inch garden hose fill valve. Note, watch the fluid, making sure the water level never drops below the flush cart suction port or runs over the top of the reservoir. Once the reservoir water level is reasonably stable or begins to increase, turn the makeup water down or off as conditions dictate. Observe the discharge water as it re-enters the reservoir. Watch for air bubbles being discharged into the reservoir. To verify possible air pockets in loop field, a deadhead process is necessary. But before we do this, mark the level of the water by adjusting the black ring on the reservoir sight glass tube. Start the deadhead process by closing the 1.5-inch flush cart return valve and monitoring the fluid level. If the fluid drop is greater than 1 inch, there is still air in the system that is being compressed by the power of the pump. Reverse the flow path or open and close the flush cart discharge valve to shock the flow and continue flushing purging activity. Continue filling and deadheading until the fluid drop is less than 1 inch. Once the water table inside the reservoir has leveled off and the air is removed from the ground loop, then flush the lines connecting the unit and the flow center. Starting with the discharge side, rotate the 3-way valves so that the off mark is at the 12 o'clock position, thereby isolating the ground loop from the flow center and the heat pump. Repeat with the return 3-way valve. This process should only take approximately 5 to 10 minutes. Once the air is removed from the unit and the flow center, we now need to flush and purge the ground loop and the unit simultaneously. Starting with the flow center return 3-way valve, rotate the off mark to the full flush position, following immediately with the discharge 3-way valve. In this position, the flush cart purges the air from the unit and the ground loop at the same time. It's recommended to purge the system in full flush position for a minimum of 2 hours. Once complete, turn the pump off and rotate the flow center 3-way valves to the off position starting with the return side. This will isolate the flush cart from the system. Be careful not to pressurize the loop. At this point, we're finished with the flow center 3-way valves and we can reinstall the plugs and protective caps. Remove hoses and flush cart connectors from the flow center. Apply white petroleum jelly to both double O-ring flow center plugs, insert the plugs, and screw on the caps. Next, we're going to fill the Geoprime 2.5 gallon reservoir. Rotate the Geoprime tank 3-way valves to the operation position. To fill, simply remove the reservoir cap and add water. Using the sight gauge, fill up to the halfway mark and then replace the cap until it clicks. The GeoLoop is now completely flushed of air and debris, and the unit is now ready for startup commissioning. It's recommended at this point to remove and clean the flush cart screen filter.
Okay, with the TAO25 that we see here, once we've checked everything and it's all installed, we want to do the commissioning. Part of the commissioning involves proper airflow. This particular unit has the electric commutated variable speed drive motor in it that maintains constant CFM against varying pressure. It comes set with the motor control interface board on normal from the factory, and with a heater installed in this unit, such as it does have, we have the choice of going up 15% on that switchboard with a switch or leaving it on normal. If we refer to the specifications for the TAO25, the blower performance data will tell us or indicate that this machine is rated at 0.6 static pressure and functions at about 900 CFM. So we can assume that that is correct in the field and ductwork is designed properly, but when you're out in the field and you want to check the airflow, the simplest method when we have a heater installed is to do temperature rise across the heater. All right, in the field, to check CFM or temperature rise across the heater, what we'll have to do is go to the existing unit. Here we show the supply air plenum and the return air plenum. Typically this will be connected to ductwork in the structure. We try to get away from the radiant heat effect of the heater, which is right here inside the top of the unit. But what we'll do today is we'll drill 2 holes, one here and one in the return. Typically we would want to get farther away from the unit itself to do this, but for illustration we'll show this. We would connect to this a temperature analyzer that would show supply and return air temperatures while it's running. Then I'll go to the disconnect, the heater disconnect, and I will open it up, remove the panel. I will take a voltmeter and measure voltage across L1 and L2 while the heater is energized. Then I will take the ammeter and I'll measure around one of the wires, black or white typically, what the amp draw is of that particular heater while it's running. I'll use the formula for CFM, sensible heat formula, which is volts times amps times the conversion of 3.413 BTUs per watt divided by a constant, in our business 1.08, times the temperature rise across the heater while it's running. When I get the biggest spread in delta T or temperature rise, I'll plug in the numbers, then I can discontinue the test and calculate mathematically what the CFM is crossing this electric heater in the emergency heat mode. When we have heat pumps, typically the heating CFM with the heater energized is a slight bit more than what we would typically see CFM per ton in the cooling cycle. Because in the cooling cycle we will have more moisture, we'll have moisture on the coil, and moisture creates friction, and thus we have less CFM being produced. But theoretically, heat pumps should blow about the same airflow in emergency heat mode as they will in typical first stage heating or second stage heating with a 2-stage compressor, or in first or second stage cooling. So now we'll set up our tools to take the measurements. Okay, so here we have, what we've done is we've energized the heater in emergency heat in this particular TAO25. With my analyzer, with my semisters in both supply and return, I can energize the dual head control here, and I can see that one temperature is approximately 74 and a half degrees. The other thermistor is giving me about 68, 69 degrees. This particular device has a function key that allows me to determine the difference in temperature, which is what I'm after. I want to find out what the largest spread is before it starts overheating or it tries to satisfy. So right now we are in the 6.5 degree range, approaching probably 7 degrees. Of course, this is dependent on the size of the heater. This is probably a small heater, and I would expect probably less than maybe 10 degrees difference in temperature. Okay, while I have the heater energized and I'm taking the temperature difference between supply and return with the acceptable tools. I'll go to the disconnect for the heater, which I've removed the panel and opened the face. I'll take my voltmeter, set it to voltage. Any brand would work out there that's commercially available. I will check across L1 and L2 with the probes. And in this particular case, I see we are pulling around 205 volts. This particular transformer can be set for 208 or for 230 volt single phase 60 hertz. In this particular case, we're around 205 volts. Simultaneously, I'll disconnect that. I'll reset my device, my voltammeter to amp draw. I'll go around one of the wires and I'll note what amperage I'm pulling. In this particular case, I'm pulling around 11, approaching 12 or so amps. I would record these somewhere, typically, in some kind of form that I would put together or just on a piece of paper, because I have to use the say approximately 11 amps that I'm pulling with the heater running, which of course includes also the blower amperage, as well as the 205 voltage drop that I saw across L1 and L2. Okay, so now that we've finished gathering the data from the disconnect where we found the operating voltage as well as the amperage of the energized heater, we go back one more time to the delta T and we see that we are somewhere around 6.5 degrees. So let's assume for illustration that we have roughly in the 6.5 degree delta T range. So now we have the three factors that we need to calculate with a formula the operating CFM across this heater. Okay, so now that we have measured our voltage drop and our disconnect and our amperage draw of our heater energized, and we've taken the delta T or temperature rise across the heaters with acceptable diagnostic tools, we use a simple formula which is CFM is equal to volts times amps times the conversion of 3.413 BTUs per watt divided by the factors we're going to multiply together in the denominator of 1.08 that considers the properties of air and the temperature rise that we saw. So if I insert the values we found, we saw around 205 volts, approximately 11 amps, and we convert it with 3.413 BTUs per watt, and that gives us approximately 7,696 BTUs coming across that energized heater. Then we multiply 1.08, our constant, times around 6.5, which is our difference in temperature we saw between supply and return. That gives us 7.02. So 7696 divided by 7.02 is around 1096, or close to 1100 CFM. Now in this particular case, I know that this machine is rated at 0.6 of an inch in its spec data, and it should be delivering approximately 950 CFM. Now if it is set on plus 15%, we could probably get this. Another situation, because we have very limited ductwork, we have very limited pressure or resistance against the airflow. So even though this blower operates against static pressure from 0 to over an inch of static pressure, I know that I'm developing at least what I think I should develop. In the field, where I have more ductwork in any particular application, the CFM would probably pull closer to what I expect it to be in the spec data. So this is the acceptable method to calculate CFM. Now what I'm trying to do ultimately is to determine CFM per ton that would be crossing the air coil of the geothermal heat pump in the cooling cycle. CFM per ton. The Air Conditioning, Heating, and Refrigeration Institute, that we follow their tenets, prescribes between 350 and 450 CFM per ton of cooling. So a lot of people say 400 CFM per ton is normal. So we're probably a little bit higher than that, but we can never be lower than 350 and theoretically not more than 450. So when all is said and done, in this particular case, I'm probably moving somewhere in the acceptable range. What that tells me in diagnostics or in this setup, in the commissioning concept, is that I have the airflow crossing the coil in the heating mode, therefore I'll most likely have it in the cooling mode. So airflow is probably not an issue for this particular machine. The next step would be to check the waterside diagnostics. Okay, so now we're going to discuss actual waterside diagnostics. With a Bosch geothermal heat pump, such as we have here, this TAO25, water is everything. Without the proper gallons per minute flowing through the coaxial heat exchanger and therefore into the ground heat exchanger, we will have no effective heat transfer. We will have no value. So what we've got to do, we made sure that hopefully that we have the right electricity and we also have the right airflow. So the next thing is to check the water side diagnostics. The last thing we want a technician to do is to connect a set of manifold gauges for refrigerant processes to this machine. It will be the very last thing, and we try to always prohibit that as much as we can. We can check pretty much everything we need to know with the water side diagnostics. So the process that we'll do is I will use available tools, a pressure gauge as well as a knife blade, some people call it that, thermometer, typically digital, and I'm going to go to the pressure temperature ports, commonly referred to as PT or peach plugs ports, that are on the entering and leaving side of the coaxial heat exchanger inside the machine. They're on the outside of it, but it's connected to the coaxial in the machine. We'll energize the unit. Now we always want to check a geothermal heat pump, whether it's after it's been running for approximately 10 to 15 minutes. The first thing that I would always do is energize it in the cooling cycle and let it run for a few minutes, even if I'm checking it in the winter. The reason for this is because in the refrigeration processes in the cooling cycle, the refrigerant that may have air and non-condensables in it hits the mechanical sieve dryer, bidirectional dryer, in the refrigerant circuit first, helping remove any condensables that might be in it. Now if I do have to check it in cooling, then I could energize it or change it from one mode to the other in the winter and check it in the heating cycle. In the heating cycle, the refrigerant will approach the operating metering device first instead of the dryer. So additionally, we want to check it in full load. Now this particular unit has a Ultratech Copeland compressor in it, which is capable of 67% first stage in heating or cooling and 100% in full stage, or Y1 and Y2. We'll always want to check the unit in the water side diagnostics in full load. That means either jumping it out or calling for it and keeping it in Y2 mode. So in this particular case, what we'll do is set up all of our components and testing equipment, and we'll refer back to the product literature for this particular unit, and then we'll energize it, in this particular case, in the cooling cycle. Now, if I'm checking in the cooling cycle, I will be determining what we refer to as heat of rejection. That is the heat that is absorbed from the airflow into the refrigerant, transferred into the fluid. If it is an open loop system, this would be only water. If it is a closed loop system, horizontal or vertical, then the fluid would be a combination probably of antifreeze and water. So we'll have some variables involved with that. Now, if I'm checking the system in the winter and I want to determine the other side, that would be referred to as heat of absorption. Some people call it heat of extraction. In that particular case, we're absorbing the heat from the earth into the fluid, transferring it into the refrigerant, rejecting the heat into the airstream. So in this particular case, we'll be checking in cooling, therefore we're determining heat of rejection.
As mentioned earlier, we like to check the water side diagnostics in the second stage of operation. We're currently operating in the second stage cooling, and a simple way to verify that the thermostat is calling for the correct mode of operation is to look at the LEDs on the ECM control board. There are LEDs outside each terminal designation, whether it be G for fan, Y1 for first stage, Y2 for second stage, and O for reversing valve operation. We can quickly look at the lights to determine the mode of operation. Now, just because the lights indicate that is the mode of operation it should be in, we always want to verify that we are in second stage mode of operation by checking the current draw on the compressor. In the second stage mode of operation, the current draw will be approximately 25% higher than it is in the first stage of operation. So once we've verified that we're in second stage of operation, we can continue with our water side diagnostics. Okay, with the unit operating, the first thing we'll do is we'll remove the caps from the PT plugs. And we'll take an insertion type thermometer and we'll insert it into the PT ports once we've lubricated the stem on the thermometer, and we'll take a temperature measurement of the water entering the coax and the water leaving the coax. Then we'll remove the thermometer we'll take our pressure gauge. We'll take the PT port adapter on the pressure gauge, and we'll also lubricate that. We'll take a pressure measurement entering the coax and a pressure measurement leaving the coax. Get our pressure drop, or our delta P, to input to it into our formula.
Okay, so what you've just seen is my counterpart Mark gathering data from the live machine. We're talking about a TAO25. We are operating it in cooling, so we're calculating heat of rejection. We want to make sure that any electric heaters are off, as well as any heat recovery package, commonly referred to as the superheater. All of these must be in the opposition. What Mark has found by taking the PT ports, or pressure temperature ports, on the coaxial entering and leaving, he has determined that the entering fluid temperature is 68 degrees. He's also determined that the leaving fluid temperature is 81. As we're talking about cooling, we're absorbing heat from the structure and rejecting it to the earth. So the temperature should be getting hotter when it leaves the coaxial. So here we have a delta T of approximately 13 degrees. That's one of the three factors we're looking for. Additionally, Mark had to gather the data with a digital psychrometer at the return. He had to determine the entering dry bulb temperature, which he found at 67, and the entering wet bulb temperature at approximately 60 degrees. Then he determined from the coaxial the entering fluid pressure and the leaving fluid pressure of 14 psi and 13 psi, so roughly he found a pressure drop, or delta P, of about 1 psig. So we take this information and we go to the current TAO25 full load data. On the middle of the right side of the page, you're going to find in the spec data fluid pressure drop. What appears closest in our data to 5.6 psi, or is 5.6 GPM at approximately 1 pound of pressure drop. Okay, remember earlier we focused on the formula used for calculating heat of rejection in the cooling cycle, and we said that that would be factors of delta T across the heat exchanger times the GPM times the brine factor. Now what we found, what Mark determined from the live equipment, was that he had approximately 13 degrees delta T, or temperature difference, from leaving to entering across the delta T, rejecting heat to the earth. We determined from the product literature that 1 psig pressure drop was equivalent to about 5.6 gallons per minute. That's just what we need as one of the factors in our formula. He also substituted for the brine factor 500, which we said earlier was water only, and that's what we were using in this particular case. If Mark had been using a glycol, antifreeze, methanol, or any other acceptable antifreeze solution with a closed loop, then he would have simply substituted 485 into the formula. So now we have all the factors to give us the answer, or 13 degrees delta T times 5.6 gallons per minute times the brine factor of 500 for this TAO25 at these conditions to determine the heat of rejection into the earth. Now the final step in determining the heat of rejection in this particular case, remembering that we have a TAO25 and we're operating in the cooling mode, what we have calculated is approximately 36,400 BTUs per hour is being rejected based on our conditions at this particular location. Now we go to the specification data, which I referred to earlier, and down here on the lower right of the TAO25 page, in full load is capacity data, full load cooling. One of the columns is labeled heat of rejection, MBTUH, thousands of BTUs per hour. Now we're talking about cooling, so we'll use this as the data to compare what we found against. Now if we had been in the heating mode, heat of absorption, we'd simply go to the right over here. Same formula, same calculation methods. So in our particular case, he determined 36,400 was actually being absorbed and rejected from the house into the earth. And if I look at the data, what closely represents the conditions we were under, which fall under entering fluid temperature, entering air temperature, dry bulb and wet bulb, and entering GPM, or GPM flowing through the heat exchanger, I have determined from the specification data that we should be operating at close to 31,000 BTUs per hour of total heat rejection. So the way to determine how well this machine is running at these particular conditions is what we found actual divided by specified. So actual at 36,400 divided by approximately 31,000 from the specs, and we come up with an answer of 1.17. We convert that to percentage by multiplying by 100%, and we are operating at approximately 117%. The Bosch criteria for cooling or heating is a minimum of operation of approximately 90% or better. So in this particular case, if a technician was in the field and checked it the way we have determined and shown you, this would be acceptable to Bosch and should be acceptable to you as well as the consumer. Whether we're operating in the cooling or heating cycle, the measurements and the calculations are the same. If we were below 90%, then we would have to think beyond the concept that maybe something is wrong with the water circuit or the air circuit or possibly the refrigerant circuit. The last thing we would want to do is put our gauges on this machine.